Okay, so let's move on to this one. This is an x cubed function. Okay, so I'm going to sketch that out. Okay, I'm going to have some general point x. This y coordinate is x cubed. I'm going to find some arbitrarily close point x plus h. And this y coordinate then must be x plus h cubed when I put it into the function. So I'm going to, before I calculate the slope at a point, here I'm going to find the general slope function or the derivative first, and then I'm going to use that slope function to calculate the slope value when I plug it into there. Okay, so there's my points. I have this slope line here, and I'm going to let the h get smaller and smaller. Those 2 points come together. I'm going to get a tangent slope or instantaneous slope. Okay, so I have to set up the limit. So the f prime is going to be equal to x plus h cubed minus x cubed over h. And I have to make sure that I put this as a limit, okay, because I need to, that's my slope ratio, but I want that slope to be instantaneous, or when that it's at a tangent point. Okay, so as I've shown before with that expansion, right, that a binomial expansion follows Pascal's triangle. So it's going to follow row 3 of Pascal's triangle, this one here. So when I expand that out, I'm going to end up with limit. Now this is good to know this shortcut, otherwise you're going to have to do the FOIL and everything. But if I know the shortcut here, I know this is going to be 1x cubed plus 3x squared h plus 3xh squared plus 1h cubed. So it's following those coefficients. Okay, so there's my expansion, minus x cubed, and that's all over my run of h. Okay, so once I have that, I can, I should be able to cancel out things. And again, notice that original x cubed cancels out because we really don't want this height. We want the height in between, right? We want that change in height anyways. So that cancels out, and I'm going to do a little bit of shortcut here because we can see that everything left has a factor of h, so those are going to cancel, and I'm going to end up with that. So then, writing this out, limit as h goes to 0. Again, it's important to keep track of your terms, but I end up with 3x squared plus 3xh plus h squared. Okay, and then I can plug in my h is 0, and I get 3x squared. Okay, so there it is. So the derivative function, f prime x, is equal to 3x squared. Okay, so then I can use this function to calculate the slope at x equals 3. So at x equals 3, the slope function calculates a slope value of, so it's just going to plug that 3 into there, 3x squared. It's going to give me a slope value of 27. So there's my slope. That's the tangent slope at x equals 3. So as at x equals 3, the tangent line is going to have a pretty steep slope. Okay, so there it is. We have, using our slope ratio, use a limit, basically bringing those points together. Since we generalize for x, we come up with a function that calculates slope. Now, one last thing before I finish up here is that, again, remember we had the changes of cubic functions at the very beginning. We looked at the changes. Changes of cubic functions were quadratic. And I want you to notice that the derivative or the change function, or the derivative function or the slope function or the rate of change function of a cubic function is quadratic. So we went from a cubic to a quadratic. And this is fairly consistent because if the cubics change as a quadratic, then the rate of change is being quadratic makes sense.